Yeah, bad boy baby, Ralph Tresvant, Big Smalls, listen. Yeah, baby. Listen to me, oh yeah.
When it comes to sex, I'm similar to the Thriller in Manila. Honeys call me bigger, the condom filler. Whether it's stiff tongue or stiff dick, Biggie squeeze it to make shit fit. Now check this shit, I got the pack of Rough Riders in the back of the Pathfinder. You know the epilogue by James Todd Smith. I get swift with the lyrical gift. Hit you with the dick, make your kidney shift.
Right. Hello? Can you all hear me? Can you hear me? You should be able to, but who knows? Let's bring up the slides. There we go. Cool. Excellent. Right. Give it another couple minutes while I go through a couple of general bits and bobs. So I'll be running this on Twitch obviously now. After it's done, maybe not immediately after, because I'll probably want to go to sleep, or at least eat something. But at some point afterwards, some point soon, maybe tomorrow, I will export it from Twitch to YouTube. So it will be on YouTube for those who aren't here. Well, if you have questions, pop them in the chat. I might not get to them immediately, but I will get to them at the end. Yes, so, what's the time? What is the time? Oh! It's a couple minutes past. What else? My mic is on voice activated. I don't particularly like doing that, but fuck holding down a push to talk key for an hour or so. So you might hear my chair squeaking or stuff like that, but you know, that you're just going to have to deal with that. Anywho, let us proceed. Yes, Radar 101, part 1. Part 2 next week, hopefully, but I'm a bit busy during the week next week, so we'll see. I've got most of it done, so hopefully we should be good for Saturday next week for part 2, but we'll see. What's the agenda for today? There will be intro, bit of a disclaimer, that kind of thing. Then we'll talk about wave properties and various basic terminology. Then we'll move on to the basics of how a radar works, echolocation, a simple sort of architecture, that kind of thing. And then we'll move on to the Doppler spectrum, and we'll have a look at a little spectrum and see what things look like in the Doppler space. And then, it's not actually here, but we will move on to continuous wave radar, and then next week will be pulse Doppler. Also, let me know in the chat if you can't see the slides moving. So if this slide hasn't changed from the sort of title screen, then let me know. But anyway, I'm going to assume that the slides are going as they should. Bit of an intro, we'll be doing a bunch of radar stuff. There shouldn't be much need for knowledge as a prereq. There won't be much maths. This is not the place to go to if you want to become a radar engineer on the cheap and you're too much of a cheapskate to go to university or whatever. This is not the place to go. There are plenty of textbooks out there if you want to kind of read up on the more quantitative side, the more vigorous side, at an introductory level. The sort of the one that they always use is Introduction to Airborne Radar, by Stimson. I think Stimson passed away, so I don't think he's actually involved in the newer editions, but it's still called Stimson's. That's the big fat book, which is all about airborne radar. What else? We will be dealing with airborne radar. Specifically, we will be dealing mostly with air intercept radar, or AIR. We will talk maybe in lecture 3 a little bit about synthetic aperture radar, but we won't spend too much time on that. And then lecture 3 we might also deal with things like multi-static radar and so on. And finally, none of this stuff is going to be sensitive in any way. It's all public domain stuff. I won't be talking about capabilities or anything like that, because that's all sensitive. This will all be sort of how radar works, not specifics of what individual radar types can do. So if you're from the GRU and you're trying to get some intel, then best look elsewhere. Right. Wave properties. We've got 4 main wave properties. The sort of most simple to explain is the amplitude. That's just the height of the peak here. This sort of green line, that's the amplitude. Actually, my cursor might not be showing up, so I'll break out the laser pointer. Here we go, laser pointer. So amplitude is this green line here, and that's just it's more or less how powerful the wave is, how loud it is, if you will. Then you have the wavelength. That is the distance in space between identical points on the wave. So we can see that here we've got a 0 and we're moving up. So it's a sort of positive 0, if you will. We go around the wave. This one is a 0, but it's going down. So it's not an identical point. We might call this a negative 0, if we will. And it comes back up again, and here we've got that positive 0 again. So this whole thing is the wavelength. And then equally, it would be the distance from here over to here, and so on. Frequency is the number of waves per second. So if you had, a 1 second period of time, how many full wavelengths are you fitting into that 1 second period? I shouldn't have used period there, because period is also specifically defined when it comes to waves, but whatever. So the frequency is related to the wavelength, where the wavelength is just the speed of the wave divided by the frequency. And frequency and wavelength are basically interchangeable as far as radar is concerned, particularly because all radar waves travel at essentially the speed of light. We'll get to that in a bit. And phase is a little more difficult to explain. Phase comes from us, instead of sort of breaking up the wave into a spatial sort of centimeters and meters sort of thing, instead of measuring it like that, let's break it up by degrees. Degrees of angle, not degrees of temperature or anything like that, degrees of angle. Because the idea is that waves are periodic, they repeat, and that is sort of like a circle. A circle sort of repeats after a certain amount of angle. After 360 degrees, the circle repeats itself. In the same way that a wave, after one full wavelength, will repeat itself. So phase, I feel, is best illustrated using what we call a phasor, PHASOR. What we do is we draw a circle where the radius of the circle is equal to the amplitude of the wave. So this distance here is equal to the amplitude of the wave, as is this distance, etc. And we draw an arrow and the arrow represents basically where we are on the wave. And on the vertical axis, we basically have the sine component of the wave, and then on the x-axis, we have the cosine component of the wave. And the way this plays in is that if we imagine the arrow is going straight along the x-axis here, so ignore this arrow and this arrow for the moment. Imagine it's going straight along here. Let's break out an actual pen. Will this work? Where is it? Here it is. So that's our phasor at the moment. As we can see, its sine component is 0. So there is 0 extent along the positive, so sine is 0. If we go back to our sine wave down here, we can see that at the start, the wave is at 0. So that's how they correspond. Where did my cursor go again? There it is. And then we increase phase as per the mathematical convention. We increase phase anti-clockwise. That's called the sense of rotation. The direction of the rotation is called the sense, and it's related to the right-hand rule and all that sort of thing. So we increase phase this way, and phase is basically just the number of degrees around this circle we're at. So we can see that at this point here, we're roughly, 1/8 of the way through. 1/8 of the way through, which puts us about here on the wave. Ish. And we can see that if that's if we call that 1, that's 1 amplitude. This is like 0.7. It's actually root 2 over 2, if you want to be specific about it. 45 degrees is root 2 over 2. But anyway, basically we can see that this distance here corresponds to this height here. And then we can see as we increase phase, we will get to a maximum at 90 degrees. So the maximum of the sine component is at 90 degrees. And then it will decrease to 0 again at 180 degrees. It will keep decreasing to negative whatever the amplitude is at 270 degrees, and then we'll go back to 0 at 360 degrees. And we can see that we go 0, maximum at, this would be 90 degrees here. I'll go back to the laser pointer so it's easier to see. So yeah, we go to 90 degrees here, we decrease to 0 at 180 degrees, down to a minimum at 270, and then back up at 360 degrees. The actual value of the phase in itself as an absolute value is of little physical importance. If you ever take a physics class that deals with waves, you'll often hear the phrase up to a phase, which is basically indicating that the actual phase really doesn't matter from a physics point of view. Because phase is just an offset along in the wave. So, a 90 degrees of phase is just shifting this entire wave sort of backwards by 90 degrees. That's all you're doing. The physics itself doesn't really change. What matters is phase differences. So if we took two waves and at a particular instant added those two waves together, if these two waves smash into each other, then the difference in the phase at the point where they meet basically determines whether they constructively interfere or whether they destructively interfere, whether they cancel each other out or whether they add to each other. So we could see that potentially if we had another wave, if we had a cosine wave potentially, which would, if we look at cosine starts at a maximum at 0 phase. So it would sort of start up here, and this is going to be very difficult to draw. Then we'll go to 0 here, minimum there, and then 0 there, and then maximum there, and so on. And we can see that if we say the two waves hit each other at this point in time, we'd see that we get this bit here added to this bit here. And you basically just get you get a value which is down here, and over here you actually get a little bit further down here. These two add together to make this, and what you get is you get slightly higher peaks when they add together like this. But yes, so we're not going to look at phase differences too much. We got not the interference patterns take importance when we look at angle tracking, which will be lecture 3, I believe. Monopulse angle tracking particularly is all based on phase differences. Actually, it's phase comparison monopulse. But yes, that's basically phase. It's one of those ones that's quite difficult to kind of explain with words. So hopefully I did a decent enough job there. Other terminology, we've got gain, which is effectively a measure of how good an antenna is at doing its job in a specific direction. So if you've got a transmitting antenna, the gain is basically a measure of how much power we transmit in a specific direction. So gain is position or direction dependent, unless we've got a perfect omnidirectional antenna. But usually we get this sort of pattern with an antenna, and we'll look at that in a moment. Wavefront is a surface in space. If we're looking at 2 dimensions, then it will be a line of constant phase. So it's the long and the short of it is that it's a measure of effectively where our wave is in space at the current time. So it's a good way of illustrating sort of how far our wave has gone, basically. And also you can use it to illustrate kind of interference patterns and that kind of thing. When we have an antenna, basically any antenna, a directional antenna at least for sure, will have a pattern of what we call lobes in gain. So the power it transmits will, as we've said, it will vary based on what direction you're taking the power in. And if the array, the antenna has been designed in any way competently, then you will have a really large amount of power going in a specific direction that the antenna is pointing in, which we call the main lobe. So this is the main lobe. In a real radar antenna, the main lobe would be a lot bigger than this. And basically, this is a diagram of sort of gain is in the sort of radial direction. So that's the gain there, that distance there. So we have one really large amount of power that's going out in the direction we are pointing, but we also have some energy going out in all the other directions, or most of the other directions. So we have what we call side lobes off to the side, and we also have back lobes going backwards. So that's what we kind of got. And side lobes, you don't really like side lobes. You want your side lobes to be as small as possible in a radar, because side lobes allow you to get jammed by off-board platforms. They introduce clutter and all that sort of stuff. So modern radars will do things like side lobe blanking and that kind of thing. And finally, duty cycle. That's basically the percentage of the time that we are taking up transmitting. So if we are transmitting for 1 second and then receiving for 1 second and then transmitting for the next second and so on, we are basically transmitting 50% of the time. So we've got a 50% duty cycle. And basically duty cycle is related to how much power we actually put out. and obviously that plays into our ability to detect things. Electromagnetic waves. So specifically, radar works in radio frequency area of the spectrum, sort of quite long wavelengths. Radar originally stood for radio detection and ranging, I believe it was, but nobody uses it as an acronym anymore. It behooves us to break the radio portion of the spectrum down into what we call bands, because it's quite a large area of the spectrum, and waves at the lower end will behave very differently than waves at the top end of the radio frequency spectrum. Helpfully, we have two sets of bands that are generally used. There's the NATO-defined ones, which we usually use in electronic warfare, and these are the ones on the left here, and they go A, B, C, D, blah. Then there are the IEEE defined ones, which are based on British, I believe, code words for, or code labels, I suppose, for the various frequency bands. And they are mainly used in actual radar engineering as opposed to EW engineering. These are the ones on the right here, and they are all over the damn place. And that comes from wartime, where they didn't want the enemy to be able to determine the relationship between the bands. They didn't want the enemy to be able to say for sure that C band is a lower frequency than L band, or vice versa. So they just jumbled them all up. A special mention goes to K band. Basically, in the air, in the atmosphere, there is water vapor, and water vapor has what's called a resonant frequency. It's basically a frequency at which water really vibes. It really vibes at that specific frequency, and that means that if water is hit with radiation of that frequency, then the water will really absorb a lot of that energy, and you will end up with heavy attenuation being a sort of absorption of your energy, and that happens to hit K band. So when they found this out, they basically created two extra bands either side of K band, KU, which stands for K under, and then KA, which is above the K band, because there are radar uses for things around here and around here, and the idea is to have quite a small K band, which specifically refers to that sort of area where you're going to get a lot of attenuation by atmospheric water vapor. We don't want a really large K band because that muddies the waters when we're discussing things, basically. K band is useful for like weather mapping radar, because you'll see basically a big black blob where clouds and that kind of thing are. Whereas things like KU and KA, those do get used for various kinds of actual military radars. Principles of radar. It works like sonar, works like how a bat's ears work. We generate a waveform somehow, somewhere in RF part of the spectrum. That gets passed to an antenna, a transmitting antenna, which radiates that out into open space. The waves hit the skin of the target, and then get reflected back and received by the receiving antenna. And that's your most basic of radar setups is that, basically. Oscillator, which generates the wave, transmit, target off over here, and then we have a receiver and some form of display so we can actually make use of what we've got. And I'm going to check chat now, because I closed it a while back and I haven't bothered opening it again. Where is it? There it is. You're going to see OBS on the right there. Text person. Yeah, it's an expensive one. Fun fact, I bought my copy from out of one of my bonuses that I got from work. So, fun fact there. Can a wave have a different below 0 to above 0? So, yes, you can have waves that go less into the negatives than they do the positives. Usually, at least for our purposes, we don't need to worry about those. We don't need to worry about that for our purposes, but you can. And it also comes into play when you do things like Fourier transforms and blah, blah, blah. X-axis on the phasor, that's just the cosine of the wave. So basically, when you get into the maths, you can represent any wave as a series of sine and cosine components, and the phasor helps relate to that. And also it basically says if you're at, say, 45 degrees of phase, if you have a sine wave, it represents this much. If you've got a cosine wave, it represents however much is on the x-axis. Right, back to the thingy. Back to that. There we go. I have a stream chat up now. Can I? No, I can't. Okay. There goes chat again. Chat goes away now. Right. I was hoping that I could have chat on half my other screen and then the sort of slideshow preview on the other half of my other screen, but apparently not. Or maybe, hang on. I can have my toolbar. Display settings. No. Okay. Screw you, PowerPoint. Nobody likes you. On to the next. Ranging using basic radar. So, radio waves, those are all electromagnetic waves, as we've seen. In Earth's atmosphere, up to a very high precision, they travel at c, which is c is technically the speed of light in a vacuum, but it's very close to the speed of light in air. And c is defined as 299,792,458 meters per second. That is the value of c precisely and exactly. It is not 1 iota more, not 1 iota less, because the meter is defined using that value. The meter is defined as the distance travelled by light in a vacuum in 299,792,458th of a second. And then the second is defined as transitions in the cesium atom. Anyway, we basically know how fast it's travelling. And we know the time between transmitting and receiving the wave. If it's a pulse, we'll get to how we know that time difference in a moment. And therefore we can easily calculate the range to the target. So if big T is the time between transmitting and receiving our wave, then big R equals CT. So that is the range, that's the distance that the wave has travelled overall. So that's the whole round trip, going out and coming back. So obviously then the actual range to the target is CT on 2. And yes, that assumes that the target hasn't moved much between us sending the wave out and us receiving the wave, but given how fast the wave's travelling, that's a fairly safe bet that it basically hasn't moved. The target basically hasn't moved between transmitting and receiving. You'll see decibels a lot as a measure of sort of power ratios, intensity ratios, all sorts of ratios. So it behooves us to at least have some form of understanding of what a decibel is. And the decibel measure is equal to 10 times log, where if you don't qualify what base it is, then you always take it to be 10, log base 10. 10 times the log base 10 of whatever ratio you're looking at. I've used P for power, but it could be whatever. As you can see here, it's often used for power or gain because it basically makes very large values much smaller, so you can fit them onto a graph and that kind of thing. And then here are some little differences here, and then it's things like, for example, so that's basically what it is. 12 is 10.8 in decibels, a ratio of 10 is 10 in decibels, a ratio of 5 is 3.2 in decibels, and so on. Radar cross-section, you'll hear that a lot. It's basically a measure of how visible something is to radar. It will depend on things like aspect. It will depend on the frequency of the radar, polarization of the radar. It depends on a lot of things. So quoting one specific value, whilst potentially informative in a general sense, is not particularly representative. The radar cross-section of an object will vary quite dramatically, particularly on aspect. I'm not going to draw a diagram because that would be quite difficult, and also I don't want to give the wrong idea of you thinking that a diagram I write is actually representative of a real aircraft or anything like that. But if you ever saw what's it called, Decker, the ones who make the JF-17, they put out a post on the forums with some example diagrams of radar cross-section plots, and those were generally decent. They looked ish right. A couple of things, they plotted it in rectilinear coordinates, as we call them, so sort of x and y, whereas real RCS plots are polar, so that the radar cross section is measured out from the center radially, rather than sort of as an x value and a y value. But they did a decent job. And some common values, you've got aircraft will be in the region of 1 to 100 meters squared ish. You can measure radar cross section in meters squared or decibels. I tend to remember them in meters squared, so that's why these are in meters squared. It's that order of magnitude. Obviously, I'm not going to say exactitudes about particular platforms. And then ground objects and also radar arrays themselves are in the region of 10,000 meters squared. The reason why I call out radar arrays themselves will come into play in lecture 3, but basically you've got to remember that radar arrays are basically a big flat piece of metal. They've got a really big radar cross-section. So radar arrays are very unstealthy, and that is why the F-117 never had a radar, along with other reasons, but it's a big reason why it never had a radar, because they couldn't make them stealthy. Doppler effect. This is basically caused by relative motion between whatever's sending the wave and whatever the wave is hitting. In the radar case, we've got two batches of Doppler shift. We've got the shift that happens on the outbound trip, where we are the transmitter and the target is the quote-unquote receiver. Obviously, it might not actually be receiving in the sense of sort of processing the radio waves we're sending out, but for the purpose of the Doppler effect, the target here is the receiver. And then on the return trip, the target is sort of transmitting, quote-unquote, the radio waves, and our receiving antenna is the receiver. So we have two sets of Doppler in a round trip. And a single set of Doppler shifts according to this formula here. We've got the received frequency is the speed of the wave, which is c, for all intents and purposes, plus the receiving velocity divided by c plus the transmitting velocity, and then all of that fraction multiplied by the transmitted frequency. And these V's basically are sort of closure rate. So we use Doppler to measure the what we call the range rate, the rate at which the target is going away from us or approaching us. It does not measure how fast the target is sort of going left or right. I'm going to take a break there. I need the lube. I will be back in a minute. I'll put some Biggie back on. Well, maybe I'll get DMCA'd. Who knows? Oh, god damn it. There we go. Let's put some Biggie back on. And also the text thingy. Back. There we move that a bit. Move. Turn that off. Okay, I'll be back in 5. Have fun with some Biggie.
Here we go, but I'm not domino. I got the funk flow to make your drawers drop slow. So recognize the dick size in these Hawkeye jeans. I wear 13s, know what I mean? I fuck around and hit you with the Hennessy dick. Mess around and go blind, don't get to see shit. The next batter, here to shatter your blatter, it doesn't matter. Skinny or fat or light skinned or black, baby, I drop these. Beneath with my knees, screaming, I poppy. I love it when they call me Big Pop, but I only smoke blunts if they roll prop. But look, I got ya caught up with the drunk flow. Fuck taekwondo, I told a fofo. For niggas getting mad cause they bitch chose me, a big black motherfucker with G. You see, all I do is separate the game from the truth. Big bang boots from the Bronx to Bolivia, getting physical like Olivia Newt. Tricks up my click dick all day with no trivia. So give me a bankroll and a bag of weed. I'm guaranteed to fuck her till her nose bleed. Even if your new man's a certified Mac, you get that H-Town in ya. You want that old thing back?
I got that old thing back.
You know.
See, baby, sit me like something. What you need, where you are, you won't believe it. You win a star.
We just screaming, they want that old thing back, like B-I-double-G-I-E, with some new R-U-L-E. Notorious, known for busting in the E-Y-E. Baby, baby, bitches know they love to hate me. I come, you come, we're coming back, so maybe how close we came to coming together is crazy. How come you and your sis make similar faces? When y'all coming, y'all be crying like I'm killing y'all bitches. I know there's a bigger picture than the camera rolling, cause I don't think y'all be knowing how this shit's unfolding. Back shots to the rear, got the Mac unloading. Gotta reload like every so often. Saying I got my swagger back, I'm looking like bitch, my swagger never left. Don't be so hard pressed to be impressed by these new rappers. They actors and the fact is, you want that old thing back.
What you wanna do?
Is my mind playing tricks like Scarface and Bushwick? Willie D having nightmares of girls killing me. She mad because what we had didn't last. I'm glad because her cousin let me hit the ass. Fuck the past, let's dwell on the 500 SL, the E and J and ginger ale. The way my pockets swell to the rim with Benjamins. Another hundred's in the crib, please send her in. I fuck non-stop, lick my lips a lot. Used to lick the clips a lot, but licking clips had to stop. Cause y'all don't know how to act when the tongue go down below. Peep the funk flow, really though. I got the cleanest, meanest, keenest. You never seen this, stroke of genius. So take off your Tim boots and your bodysuit. I mean the spandex, and hit my man next. Sex get rougher when it come to the nut buster. Pussy crusher, black nasty motherfucker. I don't chase them, I replace them. And if I'm caressing them, I'm undressing them. Fuck what you heard, who's the best in New York? Fulfilling fantasies without that nigga Mr. Rourke. Or tattoo, I got you wrapped around my dick. And when I nerd, I got the split. Shit, back shots is my position. I got you wishing, falling into mission. Fuck the kissing, licking down to your belly button. I ain't frontin'. They don't call me big for nothing. All of a sudden,
What you wanna do? I got that old thing going. What you wanna see? Baby, sit, relax and feel. What you want? You better start.
Big Diddy, y'all. Bad boy for life. You see what I'm saying, man? Once again, going to the top, baby.
Hello again. What was that one? Right. Let's go. We are back. I went to the loo. I had a swig of water. It's all good. Right. Chat. Which one? Yeah, Ross. Biggie's good. It's all good. Do like some Biggie. Right. Doppler spectrum. So our scenario is up here. Basically, that's meant to be flat terrain. The bumps are not meant to be there. That is because I was drawing with a mouse. So ignore those. Ignore those things. Just make sure that I've enabled my microphone. Yes, I did. It's all good. So what we've got is we've got basically we basically got 5 regions that we got to deal with here. We got the target. So let's step back a bit and look at what these axes are. On the right, left to right axis, the x-axis, we've got frequency, and on the vertical axis we've got power, or whatever measure you want to come up with. Our first bit right on the right hand side here is the target return, and in this scenario the target is approaching us. It is closing with us. Either that means the target is approaching us. It's coming towards us, which means it has a high Doppler shift. It's got a very high Doppler frequency, and hence it's all the way out here on the right. Next, we've got the main lobe clutter. So basically, this here is our main lobe, and as you can see, eventually it's going to hit the ground at some point. And when it hits the ground and gets reflected back, that is received as what we call main lobe clutter, or MLC. And that's right up here on the right hand side. It's big. It's a big peak because it's the main lobe, so there's a lot of power going out there. After that, we have the side lobe clutter, which we got over here. So remember, we had the main lobe and then we had the side lobes at the side. Those are going to hit the ground as well at some point. But because they aren't straight in front of us, so the main lobe is going straight in front of us, the side lobes are sort of going out to the sides, those have a sort of lower Doppler shift because they're not coming towards us at the same rate as the main lobe clutter is. Then we have the altitude return. That is a return that comes from waves that are going directly downwards from our position. Hence the term altitude return. And as long as we are travelling perfectly straight and level, we are not approaching the ground, and nor are we going away from the ground. So that means the Doppler shift is 0. So we refer, we've got this as f0. So that is the frequency at which we transmitted, and the altitude return happens at that frequency. And then we have back lobe clutter. So remember, we have lobes going backwards as well. The back lobe clutter goes over here, and because we're going away from the stuff behind us, that's why it's on the lower end of the Doppler shift. Radars will often have filters, Doppler filters, around things like the altitude return, the main lobe clutter, and so on. And you can play games with that, where if the target, currently the target's approaching us, as the target turns away from us, as it turns, its closure rate, as long as we don't speed up or anything like that, its closure rate decreases because it's going at the same speed, but now some of that speed is not pointing in our direction. So because its closure rate is decreasing, its Doppler shift is decreasing. So this return will start moving to the left. Let's have yellow show up. So it will start moving to the left here. And eventually we can see that, let's say our Doppler filter for the main lobe clutter is, oh Jesus, that went all over the damn place. It's around here. Altitude, oh my god. Wow, those filters are not very well formed, but you get the point. Eventually, the target return is going to get into this main lobe clutter filter here. Hell, even if there isn't a filter, it's going to get masked by the main lobe clutter, even if there isn't a filter. And that's what the notching maneuver is all about. The notching maneuver is all about turning perpendicular to the radar that is painting you. And by doing so, your closure rate with the radar is the same as that of the main lobe clutter, the same as the ground, basically. Because the closure rate is just equal now to the radar's velocity, the velocity of the transmitting platform. And then if you go even further, if you start turning, the full 180 and start going away, then you're going to start going into the side lobe clutter, which will sometimes have filters of its own, but sometimes does, sometimes doesn't. And then eventually, if you manage to really match your speed with that of the enemy, you're not going away from him, and you're not approaching him either, and you're going to end up in the altitude return filter. So you can play all sorts of games with that sort of thing. So that's basically what the notch maneuver does. It's also why this sort of layout is also why chaff is only really effective these days if you pair it with a sort of either a notch or some other maneuver, because what chaff does is it pops out and then it basically just falls straight down. It falls to zero velocity basically. So as soon as you pop the chaff, it's the Doppler return from the chaff is immediately going into sort of here, into the altitude return, or rather into the main lobe clutter, sorry. And it will get ignored immediately. So if you just drop chaff and keep going straight at the enemy, straight at that missile, while you're dropping chaff, and you're like, why is it not breaking lock? Then that's why. Yeah. There are things the Swedes, I believe, are doing. I think it's Saab that's doing it, where they've got they're developing these pods, chaff pods, which go out on the wingtips or sort of out under the wings on the outboard hardpoint. And the idea with those is that when the chaff gets pumped out from these pods, they get swept up into the wing vortices, and that gives them some velocity, which means that you know it's not enough that you could just keep going straight at the target still, but it means that your corresponding notch maneuver doesn't have to be quite so precise. So yeah, that's a little fun bit of trending technology. Right, on to continuous wave. What is it? It's a continuous transmission, as the name suggests. It's just transmitting the whole time, all the time. Nothing but transmit. We don't use it a huge amount in air intercept radar, for a couple of reasons. Notable exception being that CW tends to be used in supporting semi-active guided missiles. We just go into a transmit-only mode, and then the missile will be the receiver. Why don't we use it all that much in AIR? Because if we're transmitting all the time, then we can't receive on the same antenna or on the same array. So that means that the transmit and the receive antennas have to be physically, spatially separated. This is to mitigate what's called self-jamming, where the transmit is going to drown out anything we're trying to receive. And that introduces what are called swap concerns. Swap standing for size, weight, and power. On an airborne platform, especially a fighter, we are very pushed for space. We are very pushed for weight. We need to go fast, so we can't be too heavy. But we also need maximum power in order to get, large ranges, large detection ranges for BVR combat. So the swap concerns are really, really hefty in fighter aircraft especially, but also in other airborne platforms. And having to have a separate transmit and receive antenna would be killer. That we're basically halving our space to, we're halving the size of our receive antenna and we're halving the size of our transmit antenna, and neither of those is a good thing. Also, basic continuous wave doesn't really give us any range information. We can fix this, but it doesn't really give us any range information, because if we're transmitting all the time, we don't know when, even if we have a separate receiver and a separate transmitter, we don't know when the wave went out that we're receiving, because if we're transmitting the entire time, we don't know where in the wave we are receiving from. On the other hand, though, it's good because it's got a high duty cycle, 100%. If we're always transmitting, then our duty cycle is 100%. So we're putting out a lot of power downrange. So that's a good thing. How do we get range information? And also, how do we get range information when we're continually transmitting? Basically, what we need is a way to distinguish how long there has been between the point at which we transmitted and the point at which we received that particular wave. And the way we do this is by modulating the wave, so varying the waveform over time. There are a lot of methods for this. There's frequency modulation, frequency shift keying, phase shift keying, amplitude modulation, and so on. We're going to look very briefly at frequency modulated continuous wave, FMCW, specifically sawtooth modulation. If you've ever dabbled in sonar, it's similar to the FM slides that an active sonar will do. We also call this chirp because it's the waveform of a bird's chirping. So the wave looks like this. Up on the vertical axis is frequency, and the horizontal axis is time. And the way this works is if we've got orange being the transmitted waveform and then received waveform is in white. What we do is when we receive, we take the difference in frequency between at that moment what we are transmitting and at that moment what we have received. And we call that delta F. And that is related to the time shift by this frequency, formula here. C times the absolute value of the frequency shift. Forgot I had to get my laser pointer out. Divided by 2 times df by dt. So df by dt is just the slope of this modulation. So the slope of that line there, the slope of that line there is this value here. There's basically one big assumption that we make here, and the assumption is that the modulation is what's called a linear chirp, so that this modulation here is linear. It's a straight line. If it's curved, then basically this bit breaks down because df by dt varies over the course of the waveform, and you can no longer take the assumption that delta t is equal to delta f on df by dt, basically. I said we wouldn't go into much maths, but that's about as mathsy as we're going to get today. So basically we assume that this is a straight line because otherwise it becomes a lot more difficult to get from delta f to delta t. Yes. Now this picture is complicated when we have Doppler shifts involved, and what ends up having to happen, if we have a Doppler shift, what that will do is it will basically shift the white sawtooth up or down by however much the Doppler shift is. And in this particular waveform, in the sawtooth waveform, it is what we can't separate out between the delta f that is caused by the time shift and the delta f that is caused by the Doppler shift. So, you know, you can make assumptions around maybe if if we can assume the Doppler shift is very small, then we can basically ignore it. Or one of the other ways you can solve it is by switching between this FM CW and just a standard CW. So you shift between a waveform that gives you range information and a waveform that gives you Doppler information. Or what you can do is have a triangular waveform where you have it going like that. And what you do is you compare delta f on the upward slope to the delta f on the downward slope, and the time shift, if there was only delta t and there was no Doppler, then the delta f on both sides would be the same. But if you have Doppler happening, then delta f on the upward slope is going to be different than delta F on the downward slope. But that was difficult for me to draw in a way that wouldn't take 10-15 minutes to explain. So that's why we went with the chirp. Right. We're not going to look at continuous wave much from now on. It was something that was useful to explain because we'll look at pulse modulation later for pulse compression, but continuous wave itself isn't really something we're going to be dealing with until maybe right at the end of the last lecture. We might do when we're doing multi-static radars or something. Right, that is it. Next time we're going to be doing pulse Doppler, which is going to be the big one, because the vast majority of air intercept radars are pulse Doppler. So that should be next week, as I mentioned at the start. Hopefully next Saturday, same time, same place, hopefully. Questions which you can put in the chat and I will read. Let's be recorded. Yep, it will be recorded. I'll get rid of the display capture. There we go. So what Twitch does helpfully is when you've finished the stream, you can choose to export the VOD to YouTube. So that's what I tend to do. That is what I shall do. Right. Thank you very much, Athrith. Thank you very much. I tried to explain things fairly clearly. I'm going to take a swig of water. Don't mind me. There we go. Yes. Yeah, I know. To be fair, I don't stream much with copyrighted music and stuff. So as far as I've found, they've tended to just sort of on the VODs, they've just tended to mute the bit which has the copyrighted music in, because I don't do it very often. Who knows? I can always just make a second account. It's all good. So yes. If there were no other questions, then I think that will be it. What's the time? 1 hour, 3 minutes. That's actually... We made a good time. 1 hour is a good amount of time. Next week will probably be somewhat longer. There's a lot in pulse Doppler. So yes. Thank you for coming. Thank you for being here. And I will see you next time, hopefully. You all have a good day and a good week.